Dear students, today we will start next unit, content, that is third unit, time domain analysis of control systems. In time domain analysis, time response is divided into two parts. One is transient and another is steady state. So we have two parts. One is transient response and another is steady state response. We can see here for any system when input is applied, so this first part is called the transient and this second part is the steady state. So transient response is that part of the response which dies after large interval of time. But steady state response exists after large interval of time. So we have two parts. So total response CD is divided into two parts. One is transient plus another is steady state. So we can break these two responses. So first of all, we will see the response and different definitions related to response. So system response and definitions. So suppose here on y-axis we are taking output and we can take x-axis as time and y-axis as the output, and this is t. Suppose final output is represented by 1 and we have output like this, and after some time it decays. Suppose we have limits. After some time suppose here this is represented by 1.02, this is 0.98, means 2% error is there. So this is the final value. So this is the system response and we have few definitions here. Suppose this is the midpoint, where 50% of the final value is reached. And this time is called the delay time, TD. And when this value reaches to 1, and this is one time when this reaches to the maximum value, this is the rise time, PR. This is the peak time, PP. And one important parameter is here, this is the time which is called the settling time. So what is this? TD. TD is called the delay time. This is rise time. PP is the peak time, and this is the settling time. So what is delay time? First see, this is first definition. Delay time is the time required to reach 50% of the final. And rise time, this is from 0 to 100%. This is the time required to reach from 0 to 100%. And peak time is this is the time to reach the maximum or peak of the value for the first time. So this is the peak time. And what is the settling time? Settling time means when transients dies out after a large time, there is a limit. Limit means this value decays but reaches up to plus minus 2% within the final value. Then this is called the settling time. We have also 5% settling time, in which final value reaches within 5% of the final value. So this is about the definition. One thing is more, here overshoot, percent overshoot. What is percent overshoot? So this is the maximum value, maximum overshoot. This value is called the overshoot. And percent overshoot is this is represented by M. Percent overshoot is the maximum overshoot minus final value upon final value into 100. This is the percent overshoot. So this is the system response and few definitions related to this system. So we have 4 or 5 definitions. First one is the delay time. This is the time when it reaches 50% of the final value. Rise time, when it reaches from 0% to 100%. Peak, this is the time to reach for the first time for the peak value. Settling time, when value settles down within 2%. This is the settling time, and this is the overshoot. And percent of overshoot is can be obtained by simply maximum overshoot minus final value upon final value into H. And one thing more, steady state error. This is how can we define steady state error. So steady state error is the difference between required value and final value. Suppose here after some time this dies, but this is the required value, final required value, and there is some error after last time. Even this error exists after a large decay of time, then that is called the steady state error. So now we will discuss steady state error, analysis of error. So this is one very important part for the analysis of time domain systems. When we analyze errors. So next part is analysis of error. So first we will define error. Suppose here we are using summer. This is the forward gain GS, which is here we have output. This is the input. This is negative feedback, and back signal is supposed represented by GS. And after this summer, here we have signal ES. So obviously error is given by ES. This is the error. This is the difference of this RS minus PS. And RS minus PS, what is the value of this? From this part, you can write PS is CS into HS, and also from this part you can see that error is simply, since GS is CS upon ES, therefore you can write this is error is, you can also write this is CS upon GS. From here you can write error signal is CS upon GS, since GS equals output upon input, that is CS upon GS. And from this part, this GS equals input is C for this part. So this is the error signal. Now you can write here, you can replace this value. So you can write here ES equals RS minus PS, means RS minus PS, that is CS HS. Okay. And from here you can write CS equals this parts RS minus ES into GS into HS. You can transfer this ES, so you can take ES common, and you can write 1 plus GSHS equals RS. So from here you can write steady state error is given by RS divided by 1 plus GSHS. So this is the expression for error. So this is the final expression for error. Any error can be obtained by using this relation. Okay. So this is the general relation for error. And in time domain, steady state error, by definition, you can say steady state error. So the steady state error is given by limited value of E3 when t tends towards infinity. This is by definition. This is the definition of steady state error. Value of error when t tends towards infinite. And from in frequency domain, from final value theorem, you can apply here final value theorem. In time domain, yes, you can say steady state error equals limited value of ES SES when h tends towards 0. So this is the value of steady state error in frequency domain. This is the definition in time domain, and this is the definition for frequency. So now we can calculate. So you can calculate steady state error. You can also put this value, steady state error value, in this. So final expression for steady state. What is value of this? Steady state equals limited value of these and then spreads towards 0, or you can replace this with limited value of S RS upon 1 plus GSHS, where S tends towards 0. So this is the final expression for steady state error. So we can calculate steady state error by using. So this is the general expression, general formula to find out steady state error. So now steady state error for standard inputs. For standard inputs. So we have 3 standard inputs. Step input, RAM, and parabolic. three standard inputs. So this is RS is A upon S. Here for RAM, RS equals A upon S square, and for parabolic, A upon S cube. So these are three inputs for step input, ramp input, and parabolic having magnitude A. Obviously, when we are talking about parabolic input, RT suppose is given by AT square by 2. This is the value of parabolic function. This is the parabolic function, and Laplace domain is A upon S. So these are three standard inputs. Now we will calculate steady state error using this expression for all these three standard inputs. That is for step input, ramp input, and parabolic. What way? So first take step input and find out the error. So next topic for discussion is calculation of error. Calculation of errors for standard inputs and error coefficients. Here we will define error coefficients also. So first we will take for step input. When we are talking about step input, means RS is simply A upon S. Then put this value. Then what is the steady state error for this general expression? First write the general expression for steady state error. Then put this value. Put RS equals, that is A upon S divided by 1 plus GSHS. So you can write this like this: A upon 1 plus limit, this is cancelled out, and limit of this GSHS extends towards it, and this term, limit of this GSHS is called position error coefficient. Position error coefficient, or position error constant. This is also called position error constant. This term. So this is the calculation value of steady state error, and this part, limited value of this part is called Kp. So final expression for step input is, so we can write what is steady state error for step input. This is A upon 1 plus Kp. So this is the part. for steady state, where this part is called AP, which is defined as limited value of GSHS, and this is called the error constant. Okay. So this is the expression for steady. Similarly, we can obtain errors for ramp and parabolic by using this expression. This is the general expression to calculate error for any type of input. This input is a general input. You can use any standard function or any general function for RS. So you can use this expression for any type of input to calculate the steady state error. So here we have calculated steady state error for one standard input, that is called step input. So second part is error for ramp input. So procedure is same. Simply you have to replace this value. For ramp input, this is the value of RS. Then steady state error. So this is the value for steady state error. One power is cancelled and you can write this is A upon S plus GSHS. And when limited value of this is used, you can write steady state error equals A upon limited value of S GSHS, and this is KB. Another error coefficient is defined here, that is called velocity error coefficient. First one was Kp. Here Kb is defined, where Kb is limited value of this SGSHS, and this is called velocity error coefficient. This is the velocity error coefficient. So this is the another formula. Steady state error equals A upon Kb, where Kb is given by. Third one is for parabolic input. Now input is changed. So instead of RAM, we are using parabolic. Okay, this is for parabolic input. Then what is value of steady state error? Expression is same, only input is changed. So now input is changed, then steady state error can be obtained by this expression A upon S cube. Okay. 1 plus GSHS. General expression is same for all type. Only so one power is cancelled here. You can write this is the limited value of A upon S square plus S square GSHS. Okay. So the steady state error is given by when you put this value here, this will become 0, and steady state error is A upon limited value of this is square GSHS, where this tends towards 0, and this term is defined as acceleration error constant. So this is the general expression for steady state error, where this Ka is given by limited value of this, and it is called acceleration error coefficient. So this is for three types of input signals. So we have calculated the steady state error expression. This is the general expression, and then we have calculated steady state error for three types of signals. In first one, that is for step. So what is conclusion? For step input, steady state error is given by A upon 1 plus Kp, and for ramp input, steady state error is given by A upon Kv, and for third one, parabolic, steady state error is given by A upon Ka, where Kp is given by limited value of GSHS, whereas tends towards 0. Kv is limited value of SGSHS, and Ka is given by this Kp, Kv, Kp. So this is all about steady state errors. So okay, thank you. Next turn we will discuss few numerical problems based on these expressions. So this is all about theory of this steady state errors. Okay, thank you.